Summation notation. Remember this? The standard notation for writing sums in compact form. The sum of the numbers a sub m all the way to a sub n, where m is less than n, is denoted by this notation. Remember that the Greek letter sigma right here means to take the sum. This right here tells us to start the summation at j equals m, and j is called the summation index. It's also referred to as the dummy variable because any other letter can be used instead. And the number that is on top tells us to end at j equals n. And inside the summation notation, we are taking the sum of the jth term. So inside we write the general term or the function for how to find each term so that we can add up all those numbers and eventually get our sum. Let's try one. Here we need to start at k equals 4. Remember, this is j, this is the dummy variable, so they could use k, that's totally fine. That is the summation index telling us to begin at 4, at k equals 4, and to end at k equals 6. That is the sum that we're trying to find. Inside, we have the kth term, or the general term, and this is how we're going to find each value to add up. So to begin, we will plug in the start, which is 4, into our general term. 4 squared minus 2 times 4. We need to add this value to the next one. The next number after 4 is 5, so now we will plug in 5. 5 squared minus 2 times 5. And we're not done yet because we need to end at 6. So we're going to add another term where we plug in 6 for k. And now we have the sum. We just need to simplify it, where you will get 47. Linearity of summations. So if you are taking a sum or a difference of certain terms, then you can actually separate and take the sum of each individually. So you would be taking the sum starting at j equals m, ending at n, of a sub j plus the sum starting at m, ending at n, of b sub j. What if you are multiplying your general term by a constant? Then you can factor the constant out of your summation notation. And what if you are taking the sum of a constant, k, any constant, and n greater than or equal to 1? That will just equal n times k, because no matter what number you plug in, the result is k. So really, it's just how many numbers am I plugging in, or how many times am I plugging in something, and that will end up being your sum. For example, the sum from 3 to 5 of j squared plus j, you can evaluate, or you can see that it is equal to the sum of j squared from 3 to 5 plus the sum of j from 3 to 5 here, because addition is commutative. Here we will use linearity to rewrite the following sum. You don't need to evaluate it. So we're taking the sum of this is our general term, and we can actually separate that to be the sum of the first term plus the sum of our second term. You also could have written it as subtract the sum of positive 4k. We will end up factoring that negative 4 out anyways, plus the sum of your last term. In this step, let's factor out any constants that we may have. Factoring out the 9 is not going to change anything. To write nth right endpoint approximation in summation notation, to write a general term, I'm looking at what is changing between these terms. And I see the number times delta x is changing, right? Because we're starting at a plus delta x, which is our first right endpoint. So that's the right endpoint of the first rectangle. And then you have the sum of your second, and so forth onto the nth rectangle. So our general term is f of a plus j delta x. If this is my general term, then j equals 1 is the first one, right? When you plug in 1, then you get your first term. And j equals n, that is our ending point. So our sum, remember that delta x is a constant, so we can factor that out of the sum to get delta x times the sum of f of a plus j times delta x from 1 to n. And this is how we write the sum of the nth right endpoint approximation in summation notation. Similarly, we can construct left endpoint rectangles to find another area approximation. So to build left endpoints, we start at A. This time we're not starting at B, we're starting at A. I'm going to draw a vertical line from A, 0 to f of A. Continue going to the right. We do not draw a vertical line yet at B because the height of at B will not be here because we're using left endpoint rectangles. So now from each of these points, we're going to draw a horizontal line that extends toward the next line. This one you see is above the point, so we'll need to extend this vertical line. This one is below. This one again is above. So this is our final rectangle. We're using the same function as from the beginning of this lesson, so constructing left endpoint rectangles instead of right endpoint rectangles, in case you're wondering how I knew that we were going to do 5 rectangles. The left endpoints of the subintervals are a plus delta x, a plus 2 delta x. Okay, this ending one is a little bit trickier because it's not a plus n delta x. That would get us to the right endpoint. And left endpoint approximations actually go 1 delta x width less than the endpoint of your interval. So this term will actually be n minus 1 times delta x, of course, plus a. As a sum, the left endpoint sum, we will call it L sub n, and that would be delta x, the width of each of our rectangles, times the y values, the heights of each of our left endpoints. So starting with f of a plus f of a plus delta x. And in summation notation, we actually have the same general term as the right endpoints, f of a plus j delta x. But instead of starting at j equals 1, where we're starting at a plus 1 delta x, we're actually going to start at a. So what number would you plug in to just get f of a? Well, you'd plug in 0 for j. So the summation index, the starting point and our ending point are going to be different, but the general term is the same. So L sub n in summation notation is delta x times the sum of f of a plus j delta x, starting at j equals 0 and ending at j equals n minus 1. But wait, there's more. Similarly, we can construct midpoint rectangles, where the height of the first rectangle is f of a plus 1/2 delta x, to find another area approximation. Okay, so now we're going to construct midpoint rectangles. So the heights of my rectangles are at the midpoint of each interval, half of delta x for each interval. So I'm going to draw each of those points. And those are the heights of your rectangles. And the sides of your rectangles will come from those intervals. So you can build a kind of a horizontal line through each of these points. And from there, get your midpoint rectangles. That seems like it might even be a better approximation of the area. The midpoints of the subintervals are, well, they're right here, and here, and here, and here, and here. So what are those numbers? Well, this one right here would be a plus half of our width, so a plus 1/2 delta x. This one right here is 1 delta x width over, so we'll do a plus 3/2 delta x, right? A plus 1/2 delta x plus another delta x, because this distance right here is also delta x. Ooh, how do we call this one? This is a plus, similar to the left endpoint, n minus, but not -1, right? Minus only 1/2 times delta x will get you to your last midpoint subinterval. As a sum, the nth midpoint approximation we call m sub n, and that is equal to delta x, the width of each rectangle, times the height of each rectangle, which is the y value of each of our midpoints of the subintervals. To write in summation notation, we need to know our general term. To get our general term, we can actually use this to kind of help us with each of these. It looks like we're adding 1/2 x, 1/2 delta x, and then 3/2 delta x, and then it goes on from there. But if I could write that as an expression, that would be really helpful. So if our general term was f of a plus n minus 1/2 times delta x, well, first of all, if we're using j as our index, then we would need to have j somewhere in here as our input. And I'm going to replace number of subintervals with j, because we can put however many subintervals here by indicating the index and the ending point. So that doesn't need to be accounted for inside the general term. So the general term would be f of a plus j minus 1/2 delta x. And what would be our starting point? Don't forget, we do have to factor out delta x here. Our starting point, well, what j value would we need to plug in order to get this term, right? Because this is the first term. So if I plugged in 1, what would I get? Oh, 1 minus 1/2, that's 1/2. So does plugging in 1 get me the first term? Yes, it does. So my starting value would be 1. But what would my ending value be? Well, the ending value is the number of subintervals that you have created. The ending value does not need to be minus 1/2, n minus 1/2, because the minus 1/2 is taken into account in our general term. So here is the summation notation for our midpoint.